having a walk around the campus, adorned by lush greenery and splendid array of edifices. Affiliated to Mahatma Gandhi University, Kottayam, the college is a minority Christian institution governed and managed by the corporate educational agency, Syrian Catholic Diocese of Kodamangalam. In strict compliance with the vision of the founding fathers, the college has served the community irrespective of caste, creed and color, and has contributed to the world quite large number of value-based Nirmalites. Her performance in academic and non-academic activities has been acknowledged by the NIRF Rankings 2017 in the form of its position on the 91st among the list of colleges in the country. In addition, the college has been bestowed with the prestigious Star College status by the Department of Biotechnology, DBT, Government of India. The college has now grown to become a center of learning that offers graduation in 17 disciplines, post-graduation in 14, and research facility in 7. The college also runs 17 certificate diploma programs. The college attracts quality students from the length and breadth of the state. Some students come even from other states. The IGNOU Study Center, functioning in the college, offers 11 UG and 4 PG programs. The Nirmala Civil Service Academy, functioning in the college, caters to the needs of civil service aspirants. Out of 72 full-time faculty, 45 are PhD holders. 36 research guides are supervising the PhD fellows in 6 disciplines. As many as 52 research scholars have so far been awarded PhDs. 34 research projects have been completed during the last 5 years, and nearly 150 seminars and lectures were organized during the said period. The college has been successfully publishing a biannual research journal, Science and Society, for the last 15 years. The teachers publish in national and international journals and present papers in national and international seminars or conferences. The college has 6 auditoriums and 18 conference or seminar halls, of which 8 are air-conditioned. It has 34 classrooms with ICT facilities. The laboratories are equipped with modern equipments. The fully automated library offers computerized catalog search service through the library management software called LibSoft. The library provides remote access to e-resources through its digital library wing called Nirmala College Digital Library. The library has nearly 82,000 books. High-speed internet connectivity is another attraction of the campus. The college has a favorable student-computer ratio of 6.27 with 431 computer terminals spread over 8 computer labs. The English language laboratory with 30 web-enabled computers is a center for training students in the use of correct English. We do have sufficient playgrounds for the physical training of the students. Our students do excel in the field of football, handball, judo, taekwondo, chess, etc. In cultural activities also, our students win coveted positions in university youth festivals. The college has well-furnished guest house with 15 rooms, 4 ladies hostels, 1 boys hostel, 2 sports hostels, fitness center, reprographic center, yoga center, digital theater, recording studio, folklore museum, public call center, stationery store, kiosks, cafeteria, post office, bank, 2 ATM centers, health center, herbal garden, butterfly garden, vermicompost plants, biogas units, aquatic farm, mushroom farm, rainwater harvesting unit, solar panels, staff cooperative society, prayer hall, special amenities for the differently abled, career guidance and placement cell, NSS and NCC. Blessed by the Almighty, the college is marching towards greater heights. On the occasion of completing 65 glorious years in service of the nation, we salute our forefathers who made this institution great through their hard efforts and seek the support and blessings of everyone in rejuvenating our future. Nirmala College, Muvattupuzha, established in
with unswerving curiosity and inquisitiveness. Reverend Dr. Mathew Thottiyil was a very lovable personality, artless and naive to the core with no pretensions. He was called his heavenly abode on 10th November 2000, leaving abode in the hearts of many. Moving to the official inaugural ceremony, I would like to invite Professor Philip Augustine, Head of the Chemistry Department, to deliver the welcome speech.
Good morning, all. Nirmala College Muvattupuzha is managed by the Catholic Diocese of Kodamangalam. It started in the year 1953, and the Department of Chemistry was started in 1957 with the induction of the BSc Chemistry course. And in 1967, the department was raised to a PG department with the induction of MSc Chemistry. And in 1988, the department became a research department. And regarding Reverend Dr. Mathew Thottiyil, Reverend Dr. Mathew Thottiyil, PhD from Manchester University in 1965, and he joined the Department of Chemistry as a lecturer, and later became the HOD of the department. And towards the end of his tenure, he became the principal of Nirmala College, Muvattupuzha. After the demise of Endowment lecture, and this lecture is carried out in November, because November 10th is the Remembrance Day of Dr. Mathew Thottiyil. Chief guest of the day, Subi Jacob George. He is the prestigious Shanti Swarup Bhattacharya Award 2020, and he has consented to deliver the lecture, and we are very proud to have such an eminent scientist, the Reverend Dr. Mathew Thottiyil Endowment Lecture. And on this occasion, a very hearty welcome to Dr. Subi Jacob George to Nirmala College, Muvattupuzha. And on this occasion, I extend my hearty welcome to our beloved principal, Dr. K.V. Thomas, who is the person regarding the development of this Nirmala College, Muvattupuzha. I extend a hearty welcome to Dr. K.V. Thomas, our principal. I extend my hearty welcome to the former faculty members of the chemistry department and members of other departments who took pain to establish such an endowment lecture on the name of Reverend Dr. Mathew Thottiyil. A hearty welcome to all our former faculty members of this college. And I welcome other dignitaries from other institutions, scientists, teachers, professors, PG students, all. I extend a hearty welcome to all. And I extend a hearty welcome to my colleagues, especially Kutanapallil, who is the coordinator of this endowment lecture. I extend a hearty welcome to all the students of Nirmala College and other colleges. And with these words, I conclude. Thank you very much.
Thank you, Philip, sir. Now I really invite our beloved principal, Dr. K.V. Thomas, to deliver the presidential address.
Resource person, Professor Subi Jacob George, Professor Philip Augustine, Head of the Department of Chemistry, dear teachers, well-wishers, and students. I am honored to address you all on this occasion of the Memorial Endowment Lecture of Reverend Dr. Mathew Thottiyil, former principal of Nirmala College, Muvattupuzha. I was a student of this institution while he was retiring. I was blessed to maintain acquaintance with him after his retirement, as he served as my parish priest right after his retirement. He used to visit my home time to time, and we had long conversations occasionally. He was a simple and a humble person throughout his life. I take this opportunity to remember him with deep gratitude and love, and also thank him for all his contributions towards the development of Nirmala College and especially the Department of Chemistry. Let us pray for the departed soul and seek his blessing for all the future endeavors of this institution. Today, we are blessed with the presence of a great personality, Professor Subi Jacob George, to address all of us. For the 20th Reverend Dr. Mathew Thottiyil Memorial Seminar on Dynamic Chemistry Beyond Molecules. I take this opportunity to congratulate him for the achievement of the prestigious Sagar Prize for his contribution towards science and technology in chemical sciences for the year 2020. He is also a recipient of many other awards. He is an active scientist and also got a rare opportunity, and we also got a rare opportunity to listen to his lecture. I thank him for spending his valuable time with us today and for an inspiring lecture going to give right now. I also congratulate all the faculty members of the chemistry department, especially the coordinator, Jyoti sir, and the head of the department. This webinar also with a right. Also,
I think there is a network issue. Now, let's move to the main session. I invite Sister Emmy Tomey, Assistant Professor of Nirmala College, to introduce the speaker.
Good morning, one and all. This morning, we are blessed to have with us an eminent personality to deliver today's lecture. George is currently the Professor and Associate Chair of the new Chemistry Unit, JANSER, Bangalore. Professor Subir George is the recipient of the prestigious Chandni Swarup Bhatnagar Prize of Science and Technology in Chemical Sciences category in the year 2020. He obtained PhD degree in chemistry from the National Institute for Interdisciplinary Science and Technology under the guidance of Professor A. Ajay Ghosh in 2004.
Jacob George to present today's session. Welcome, sir.
Thank you. Thank you so much, and good morning, everyone. Respected Principal Dr. Gaby Thomas, Professor Philip Augustine, Head of the Chemistry Department, Sister Amy Tommy, dear teachers, my dear friend Jyotish, and also all the students. It's a great honor to be here and to deliver this Reverend Dr. Mathew Thottiyil Memorial Lecture, because I can see that he has contributed immensely to the growth of Nirmala College and also the education in that area. So it's very important because I'm also around, my hometown is also very nearby. I'm from Pirava. So that way I'm like, Muvattupuzha is very close to me, close to my hometown. So it's a great feeling to be here and very happy and humbled and honored to be giving these lectures. And also take this opportunity to thank Jyotish, who is a good friend of mine, for inviting me to this seminar. So considering the broad audience, what I will do, probably, I know that I was told that also undergraduate students are attending, master's students are attending. So I think probably what I will do is to give a flavor of this subject, which I'm going to talk about without going in deep into my research area. I would like to see most of you till the end of my talk. So what I will try to do is kind of give a kind of flavor why we are doing this subject and what are the opportunities and where this field is going. So I'll be keeping in that aspect, and I request all the students to be around and ask, definitely write questions in the chat box so that we can have a nice discussion or nice interactions at the end of my talk. So let me share my slide, and please alert me if you have any difficulty to hear or see the slides. So let me share my slides. Can you see the slides?
Yes, sir.
Yeah. Okay, so this is the first slide. I'm like, so I will be talking about the dynamic chemistry beyond the molecule, and I'll come back to that in a moment. But then dynamic chemistry beyond the molecule is basically what we are talking about, something called supramolecular chemistry. And supramolecular chemistry is a kind of, as all of you know, is a new branch of chemistry, and probably which got a lot of attention in probably last 2 to 3 decades. And it has a lot of applications, and it's an emerging field. And this particular video is to give a kind of flavor, what is the kind of material I'm going to talk about. But then I will come back to this video a little later. But then I thought today is a very nice day because all of you know it's a Children's Day, and it is November 14th. And it's something very important for our institute because Jawaharlal Nehru Center for Advanced Scientific Research, that is JNCSR, which started in 1989. Basically to celebrate 100th birth anniversary of Chachaji. Today, so special for us. Just I thought it's a coincidence that I'm giving a talk on November 14th, and this figure, Professor Sena Rao. So he started this particular institute in 1999. That time, 1989, he was the scientific chairman of the scientific advisory committee to the Prime Minister. So that time, this institute started. Now it's almost like 30 years. We are one of the leading institute working on interfaces of chemistry with materials and biology. So let me go on with these introductions to my group. So we have a group in Bangalore. I joined here in 2008. So we are basically kind of organic synthetic chemist. We work on materials, and one aspect we work is like a supramolecular chemistry, as you can see here. So that's what I am going to talk about. And we have various research areas. I don't want you to get confused with this. I will be talking only about one class of material, that is about dynamic supramolecular polymers today. And before I do that, I'll be going through the basics aspects of dynamic chemistry beyond molecules, why we are doing it. And before I end the talk, I'll talk about this particular class of material. So let me start very simple. We all know that something which always supramolecular chemistry is coined as the chemistry beyond the molecule. And we always say that our inspiration comes from nature. Okay, and we know that at this point we are not in a position to create a life. And although even at some point of time, even it will be difficult for us to define a life. What we know that is probably the smallest component in a life is a cell, and probably it is also very clear that probably we cannot also even make a cell probably in next 2 centuries. But something which we can do is at least take kind of cell as an inspiration and look into various components in a cell and try to synthesize or try to create them artificially, so that probably we can create a large number of interesting materials. So what my point is, if you look into this cell, it's probably one of the most complex entity in the universe. Doesn't matter, irrespective of the size, even compared to the galaxy or kind of atoms, probably this is most complex entity, because you can see that for a cell to be active, there are large number of components inside the cell which are working tandem, parallelly, everything, and then that is actually the origin of life. But when you look into the cell, there are 2 important aspects. So if you want to, as I mentioned, don't misunderstand that the objective of our research is not to create a cell, but to take an inspiration from the cell and to make biomimetic materials. And in that aspect, if you look into this cell, its structural aspects, there are 2 important aspects. One is this side, that is assembly, that is beyond the molecule. What I mean is that if you look into the cell, most of the important functions are performed by not individual molecules, but it's always an assembly of molecules. There are multiple examples. If you look into DNA, all of you know that DNA is not a single molecule. DNA is a double standard, so it's more than one molecule. Let's talk about anything like a cell membranes, right? They are also assembly of lipid molecules. And if you take examples like tobacco mosaic virus or many of the proteins responsible for our motion, like actin movement, like actin proteins, motor proteins, if you look into it, they are all assembly of proteins. So monomers of proteins are assembled and forming large structures. So that's one of the first structural insight we get it from a cell. It's never a single molecule, although there are single molecules in the cell which performs interesting functions. But there are, most of the time, it's an assembly of molecules which creates most of the important functions of a cell. So that aspect, one of the aspects probably we can inspire from nature. So we need to learn how to organize the molecules to go from one molecule to kind of higher, large number of molecules organized in a nice fashion to perform a function. So that's one of the probably first learning lessons we can take it from nature. And probably another aspect is the nature. If you look into the cellular world, especially, it's never at equilibrium. It's always dynamic. It's always moving. So this is one of the videos, you can take it from YouTube, Inner Life of a Cell, made by Harvard University professors, to give a flavor how complex is a kind of inside our cellular life. So if you look into it, this is a kind of microtubule proteins. They're continuously assembling, disassembling, and so on. So although we tell all of our, we always advise be at equilibrium, but then if we are at equilibrium, we are done, right? So in the system, most of the, again, exceptions are there. When I say most of them, there are always exceptions, but most of these entities or most of these compartments of a cell, they're never at equilibrium. They are always away from equilibrium. So as a result, they are always dynamic. Dynamic means they continuously move. So these are the probably 2 important aspects of a cell, which I consider, or a supramolecular chemist consider, is nice properties to be mimicked in a synthetic material. And if we are in a position to mimic these things in a synthetic material, we can create smart materials. Okay, so I just told you this as a kind of introduction. So let's take this as a cell as an inspiration, or biological world as an inspiration, and trying to see whether we can make smart materials out of it. Okay, so let's talk one by one. Then I will go to my material, the kind of materials we work on. So let's see how we can assemble molecules. Okay, so if you look into it, that was the beginning of supramolecular chemistry, which is one of the most important branch of chemistry nowadays, and which got Nobel Prize in 1987. I'm sure most of the master's students are aware of it because this is part of the syllabus. The supramolecular chemistry has, my understanding, is part of the syllabus now. So so supramolecular chemistry originated because of these three gentlemen who got Nobel Prize in 1987: Donald Cram, Jean-Marie Lin, and Charles Pedersen. So their attempt was to build complexes. That means more than one molecule. Can we go beyond one molecule? And that is why the chemistry beyond molecules, which is coined by Jean-Marie Lehn. So he defined supramolecular chemistry as chemistry beyond the molecules. And if you look into the kind of molecules they created, they are kind of host molecule for guest systems. For example, guest principle behind the starting of supramolecular chemistry, the molecular recognition, the size and shape indeed matters. Okay, so this is, I just told you, like, this is the way supramolecular chemistry started, and this was probably the first attempt to assemble molecules to a kind of bigger structures, right? And this I always show. I'm like, people, most of the students ask the concern always, these interactions are so small, but still they are able to stabilize very bigger structures. And one of the important concept behind is kind of cooperativity. All of you know about the story of Gulliver. So they are just like human beings. I'm like, non-covalent bonds are just like human beings. If they are alone, they are very weak. But when they are in a group, it's not easy to break them. So they're just like a human behavior. So in scientific terms, it's called as cooperativity. That means when they come together, their cooperative interactions are much stronger than individual interactions. So that way they are able to stabilize these bigger structures. Okay, so that is a kind of very vague introduction of supramolecular chemistry. And you see that, as I told, this field has started in 1980s. But if you look into probably another 20 or 30 years of this research on this host case chemistry, this has evolved to a greater extent, and you can also make very big host systems where you can even think about doing reactions inside these host systems. This is one of the beautiful cage created by Fujita. So my point is that it's no longer, we started calling it, all of you know that organic synthesis or covalent synthesis is well known, but people started terminology kind of non-covalent synthesis. We can even think about non-covalent synthesis to make such bigger structures. So this is all about the assembly of molecules. The bottom message I would like to give you is we are in a position, supramolecular chemists are in a position, just like similar to nature, we can make weak interactions. We can make use of the weak interactions to make assembled molecules and make materials. So probably this is the best bottom-up approach to synthesize nanomaterials, right? We can think about keep on building up the structures to higher, to finally to create a material starting from the molecules. So this I will skip it. What about the motion? When you must be remembering that when I showed you the structure of a cell, I picked up two important aspects of it. One was the organization beyond molecule, and probably the other one is more like a assembly. That means it's always under dynamic. And what was the chemist's first attempt to mimic a dynamics or mimic a movement that led again to a Nobel Prize in 3-4 years back in 2016? All of you know, Sauvage, Fraser Stoddart, and Benferinga got Nobel Prize for molecular machines. Right, so the molecular machines probably is the first attempt from a chemist's point of view to mimic a movement. Can we create molecules synthetic molecules to move, or can we make them to perform a work? So that was the first priority. A first objective of these molecular machines. And this is again, you can see that this is inspired from nature. If you look into the bacterioflagellum motors or movement of an actin protein and so on, which is important for the muscle action. These are all kind of these are kind of good inspirations to work on this particular field of molecular machines, where probably we can mimic such rotary motion or a translational motion by using synthetic molecules, which are on continuously motion. And this started with Fraser Stoddart on this kind of supramolecular system. Again, you can see that this is more than one molecule. This is a kind of schematic of the kind of molecules he worked on, rotexins and catenins. Please don't worry, I'm sure some of you have definitely heard about these things. But that's why this was initially considered as a branch of supramolecular chemistry, also molecular machine. I just show you one video to really convince you, because this is nice schematic that will not convince you that molecule can indeed perform function. So one of the earlier, probably in early 2000, 2001, 2002, probably Benferinga came up with a wonderful system. So you know that a molecule to move, you need a fuel. And for a chemist, the fuel could be a chemical reaction or a redox reaction or a kind of enzymatic reaction similar to the nature, or it could be light. Light can also provide a lot of energy to the molecule to move. And probably this was Benferinga's creation. He came up with a kind of molecular machine which is responsive to light. If you shine light on it, it will start rotating just like the bacterioflagellum motor I showed here. So just to convince everyone that indeed they are able to move or rotate, and they are indeed able to perform a function or to perform a work. This particular video at the bottom left, you can see that what he has done is he has functionalized a surface full of these molecular motors which are responsive to light, and he started shining light, and he put a piece of small gold nanorod on that surface, and as you can see that gold nanorod start rotating when you shine light. So that is a clear indication that when you shine light, molecular motor starts rotating, and they are able to perform a work by rotating a kind of nanorod put on top of that molecular machines. So I know that this is one Nobel Prize which is highly criticized by people, because for a simple reasons, they say that generally Nobel Prize is given to those chemistry which has influenced the society directly. So that way this was highly criticized, because this is a wonderful chemistry, but all of you know that we cannot go into a market and buy a molecular machine, right? So probably that way this was criticized, but this is beautiful chemistry. I still appreciate, because probably this is the first time to mimic the dynamic motion of a nature or a cell. People are trying to make molecules move in particular direction, right? And this was, since it was criticized, people, so they tried to, because the criticism is, will they ever work in reality? And you see that principle looking into nature, the dynamic aspects of nature can also be, to a certain extent, you can mimic in synthetic molecules. Okay, these are the two aspects. But then that brings to my system, our own research. So far, I gave you a kind of background of supramolecular chemistry, or you understood what I mean by the dynamic chemistry beyond the molecule, right? So we are talking about chemistry, which is dynamic chemistry in the sense the molecules are always under dynamics, but then it's not at the molecular level, but we are talking about a supramolecular level, or it's a chemistry beyond the molecule, right? So now I ask you to look back to this particular video where we describe the inner life of a cell. As I mentioned, that YouTube video, if you can just check it in YouTube, you'll find this. You see that this is again the microtubule assembly and disassembly process, and which is responsible for the muscle actions and the movement and everything. But then if you look into the assembly disassembly process, or if you look into the dynamics of the process, it's at a higher length scale. You see that unlike the molecular machines, which happens at a kind of small molecular level, you're talking about micrometer long or few nanometers long, the microtubules, which has probably 600, 700 nanometers long. So the thing is, you see that the entire structure is assembling and disassembling. So what my point is, we are talking the movement, real movement in the cells most of the time comes from a kind of dynamics or assembly process, disassembly process at a higher length scales, not at a molecular level. So can we mimic something like that? And probably if we can mimic something like that, probably that's a way to make an interesting material or a smart material. All of you agree, right? And I wish all of you are with me. Just keep ready with your questions. I'll be very happy to answer. Especially I'm looking forward to really tough questions from the students' side. Please ask any, let it be any stupid question, but please ask. So now come back to that. That's the video which I showed in the first slide of my talk. So this is what I'm calling as a kind of supramolecular polymer. And I'm sure all of you know what is a polymer or plastic, starting from this polyethylene terephthalate of acaphenum bottle in front of you. They're all polymers and they're plastics, right? But then you know the polymeric structure also, right? Polymer structure is basically, and all of you we are all from a kind of land of rubber, natural rubber, all of you know. This is also a polymer. But then if you know the structure, this has a monomeric structure, monomers or repeating unit, which is linked by covalent bonds and make large chains of polymeric chains, right? That is basically a plastic or a polymer. But then think about a situation. These plastics or these polymers are formed by not covalent bonds. By whatever we discussed so far, can we make them with non-covalent bonds or very weak bonds? Can we link these monomeric units by weak bonds? So that's something that is what this video says. This is a small molecules. You can see that there's a benzene ring and 3 amide groups at the periphery, and you know that amide groups can form hydrogen bonding with next molecules, and they can form organized into one-dimensional structures like this. And you see that this structure very similar looking to a kind of long polymeric chain, but the only difference is the monomers are held together by weak interactions. So as a result, one can expect that since they are held together by weak interactions, you can expect that there will be under dynamics, right? Weak interactions are very needed big activation energy to break weak interactions. So what happens is the monomers are always in a kind of equilibrium between the bigger structures and the surroundings. That means I would say that monomers are in a kind of exchange, and there is an exchange dynamics happens, and that exchange dynamics depends the time scale, like whether it's in the millisecond time scale or even in the second time scales or an hour or an year, depends on the molecular systems we work on. Okay, but the take-home message again is there's a kind of exchange dynamics happens. So the monomers will be going out and coming out from this long chains. So that is something, a picture of a supramolecular polymer. In graphics, it looks great, but then there are a lot of challenges to make these structures. But my point is, this is a kind of material I'm going to talk about. So why we want to work on this kind of supramolecular polymers? You can imagine that we know that the polymers, a world without polymers is a kind of a world without life now, because we cannot live without polymers. That's the kind of situation we are in now. But at the same time, since if they are making with covalent bonds, you can imagine that they are very stable, and we know that that's one of the things they will take long time to degrade, and all the polymers cannot be degraded. Only a certain kind of polymers can be degraded using biodegradable techniques and so on. But then plastic waste is a kind of it's a serious sustainability issue, right? It's polluting our environment. So what's the way out? Is this a way out? I'm not saying that this is a way out. This is probably one way to think about can we create a polymer which is linked together by very weak bonds. And then whenever you don't want a polymer, we can think about taking back to the monomer because we know that these weak bonds are easy to break. We probably certain processing conditions we can bring back the monomer, and probably we can reuse it completely again for a same purpose or a different purpose. So in that terms, you can think about a concept called not biodegradable plastic, a concept called recyclable plastics. In the sense, you are going to recover the monomer and reprocess it completely. Okay, that's probably a very important aspect in terms of a circular economy. But let's not go into that far, because this field is probably kind of 2 decades old, and there are still so many challenges before we think about it, to see them probably in real applications. But my objective is to introduce you to this particular class of molecules or particular class of polymers, so that many good ideas can come from the young minds sitting there. So why we want to make one objective, obviously I told, could be a recyclable plastic. Is there any other advantage? I'm sure the students have watched this video, watched this movie, Terminator, and then you see that it would be nice. It can self-heal. What is self-healing? If there is a damage in your material, can it come back to the original shape with the original mechanical strength? So that's something is possible if you look into these structures, because what my point is that the monomers are always under dynamic conditions, right? So if you break the polymer, probably because of this dynamics, it has a tendency to self-repair itself, and probably regain the original shape of the material. So again, let me tell you, this is self-repairing mechanism, again, is a wonderful technique of our nature or biological world, right? There is a self-repairing mechanism always in the biological world. So probably this is another aspect one can learn from biology and probably mimic in a material to make a smarter material. So this is probably the one aspect of it. We'll come back to that. But then all of you know that this 2020 is the year where we celebrate 100 years of the birth of polymers. Because unlike organic chemistry, because if you look into organic chemistry, you know that 1828 is the first molecule, urea, came into picture. And most of the development in organic chemistry happened after that. But you know that polymers were in use even from Columbus' time. People were making bags and everything with rubber. But no one knew that the structure of that material. It was only in 1920 people really proposed. The person who proposed is Hermann Staudinger, really proposed the polymers are indeed big macromolecules linked together by small molecules. And that is why Hermann Staudinger got Nobel Prize in 1953. But at the same time, the one important person is Wallace Carothers, who is actually associated with Staudinger, who started synthesizing this polymer in the lab. We always call him as the father of synthetic polymer science. But he did not get Nobel Prize because he died at a very young age. At the age of 40, he committed suicide. But then if you look into most of the synthetic polymers, even now we use, like a nylon 6,6, polyethylene terephthalate, all are contributions from this gentleman, Wallace Carothers. So when we talk about Staudinger, another name to be remembered is Wallace Carothers, because his contributions are immense to the development of polymer chemistry. Why I talked about this? Because just to tell you that this is probably an appropriate occasion to talk about a completely different polymeric material, which is more smart, probably, which are reversible. Probably this is a kind of perfect tribute to this celebration of 100 years of macromolecular chemistry. So we know that polymers are everywhere. Since I am really running out of time, so my point, just one thing I wanted to say that it's very simple, right? I mean, if you look into schematics, as one probably if you look into it, it's very easy to make supramolecular polymer, right? You need 2 molecules, or you need monomer with a kind of binding groups which can bring together molecules like the one I showed in a kind of amide hydrogen bonding and so on. But it was not so easy as that, because one of the problem is any polymeric properties is determined by its molecular weight. You know that the longer the molecular weight of a polymer, or longer the length of that polymeric chain, the better is its mechanical properties. So to get a high degree of polymerization or high molecular weight, one of the challenge was that this is the x-axis, I'm talking about the association constant. Association constant is the energy between 2 molecules interact. For example, if you take water molecules, the association energy will be somewhere around here. And if you take a carboxylic acid molecules like benzoic acid, we know that it can form a hydrogen bonded dimer. The association constant is somewhere around 10 to the power 2. So you can imagine, and if you take DNA, you know that there are hydrogen bonding motifs, AT and GC pairs adenosine, thymine, and GC pairs, it has an association constant of somewhere around 10 to the power 3. So you can see that the real challenge, this was a theoretical study, but the real challenge is to make it something like 10,000 molecular weight, you need a very high association constant organic motif. This was one of the challenges at the early stages. So you can see that we need to make something better than nature if you want to make a kind of supramolecular polymer. So that was one of the challenges, but then obviously I would not have shown this field if it does not exist, right? So people could succeed in making association constant as high as 10 to the power 7. This is a moiety called uridopyrimidone. You can see it here. Don't worry about the names, but you can see that there are like 4 hydrogen bonds in this. You can see that 1, 2, 3, 4 hydrogen bonds are there, and they are very strong, which has a very high association constant of 10 to the power 7, much higher than even the DNA base pairs. So we can make polymer out of these materials. And then I just wanted to show that this particular system, because this already a company called Suprapolix is selling this material. And you can see that this is their demo video, their kind of sale promoting video. I'm not part of this company. Don't think that any conflict is there. So I'm saying that, so you can see that if you take a polymer made up of this material, and if you cut it into 2 pieces, okay, so that's what you would be immediately seeing it. You can see that it is cut into 2 pieces. Okay, as I told you, keep it in mind. Just visualize that real picture. The molecules are really under dynamic conditions. So I put it back. But what happens is that this dynamics will help some of the molecules from that side to move this side, move this from that to side, and basically you self-repair it completely. And you can see that it can hold the same mechanical properties. It can hold the same amount of weight as before. Isn't it nice? So probably this is one of the advantages. And you think about a coating, like your car paint or something, you made a scratch. And you know that when you have especially an expensive car, it really hurts, right? If you have a scratch on your car. But think about a situation where you have a paint which completely self-heals. And then again, probably due to the dynamic motion of these molecules. And probably these are the kind of applications, supramolecular polymers, because of that dynamic property, one can imagine about it. And then probably that also provides a kind of another possibility of completely recyclable polymers, where we can completely take back the monomers to the initial stage and reprocess it and so on. So this is one again trying to introduce the concept of supramolecular polymer. And the question always people ask, I'm sure the students also will be asking this question, are they similar to the classical covalent polymers? Because they are made up of weak bonds. I will keep those concerns towards the end of the talk when you have questions, okay? But then let me tell you, it has the mechanical properties similar to the classical polymers, at least certain kind of polymers. So if you are making something kind of for mechanical applications, you can indeed modulate your structures and making such mechanical properties and so on. And one important other aspect, so you know that in, I don't know whether you study polymer chemistry at the undergraduate level, but then there are 2 types of mechanisms. One is step polymerization and other one is chain polymerization. And the striking impact which has happened in this field is like probably 10 years back, people realized that similar mechanisms also exist in supramolecular polymer. Okay, so that's an important that's very important point, because without that you cannot synthesize polymers right the way you want. Okay, you should know the mechanism of polymerization, and exactly similar to the step polymerization and chain polymerization, we have similar mechanisms in classical polymerization. So supramolecular polymerization. So that just again, I'm not going to the details because I see probably I have another 10 minutes or 10 minutes probably to wind up my talk. So this is another aspect. That's the way supramolecular polymers developed. So you can see that in all aspects is very similar to the classical polymers, but with the added advantage that they are always under dynamic. Right? So this field has active for last 20 years. And then, as I told, the first challenge in this field, probably which happened 1995 to 2005, was to identify those motifs which has a very high association constant, so that you can make stronger materials with the self-healing properties. And there was an era like 2005 to 2010, where we could really kind of think about in terms of mechanism of formation. The people realized that this kind of materials has almost similar properties or similar mechanistic properties as that of the classical polymers. And then there comes the era where I'm talking about, where we made a lot of contributions in this field. It's like last 2010 to 2015 or even now, that making use of these mechanistic insights to get a control on the properties, like a control on the structure, If you think about a polymer, the control on the structure is control its polymerization length, control its dispersity, control its sequence. Can we go to multi-component systems? These are the aspects we work on. And one important aspect, this is something which we really did recently, to again look back to nature and to get principles from nature. And all of you know that this is a kind of energy landscape of any material. I mean, this is probably true with any material, but I'm talking in terms of supramolecular polymers. And if you look into, you know that most of the materials, if you want to form, the basic principle is that you need to gain energy, right? That is, you have to lower the energy, and then that's why most of the synthetic polymeric system, because they are highly dynamic, they will easily end up in the most stable state, that is the thermodynamic equilibrium state. Okay, it will not, once it forms, it's stable there. And sometimes it can get trapped in a kind of metastable state, but then since the molecules are dynamic, it will easily skip into the thermodynamic equilibrium. But then again, look back again, these videos keep coming. I know that this is microtubule assembly. How these biological structures work, or how biological self-assemblies work. So there are examples of kind of stable structures, like if you take the cell membranes and everything, they are examples of metastable or thermodynamic equilibrium structures. But most of the other, again, filamental proteins or everything, they are never at thermodynamic equilibrium. They are always, people call it as out of equilibrium. That means the assembled state is a kind of not an equilibrium state, it's an out of equilibrium state. And you need a continuous supply of energy or a fuel for this molecule to exist in this assembled state. And once the fuel or energy runs out, it will come back to the thermodynamic state. And this is the non-equilibrium state, is the state which is more functional for these biological structures. And that is a state where they perform most of the work, like cell division, cell motility, signal transduction, anything you take it, this is a non-equilibrium state of these assemblies which performs this function. And once this fuel runs out, it comes back to the ground state. So this is something different, right? I'm like, this is against what we think. I'm like, we think it's better to be at equilibrium, but in our biological world, it is never at equilibrium. And like the Nobel laureate told Prionin, who came up with the non-equilibrium statistical thermodynamic principle, he told, equilibrium is death, right? So can we make such out of equilibrium materials? And you must be wondering why you want to do it. Okay. Anyway, we are not going to make cell, but why do you want to make out of equilibrium materials? And one of the ways we can think about is, if you are able to make this out of equilibrium materials, probably that's a way to make smart materials. Because so far we see that we have worked on equilibrium materials, which is in the blue component. I would say that, which is important for various applications. I'm not saying that they are not important. They are most important for various applications. But then if you want to make more smart materials, or if you want to think more like a nature's way, or a kind of biological way, we need to think about non-equilibrium materials. And probably that is a way to make dynamic materials, adaptive materials, living materials probably, and at some point of time, really smart, really smart materials like thinking materials, right? So probably that's the one way to go from equilibrium to out of equilibrium. I just wanted to introduce this concept to you. So recently what we have tried to do is to learn the biological self-assembled principles into synthetic materials, because another aspect, if you look into the biological, they are very monodispersed. That means they are well defined. We were trying to see whether we can make such materials synthetically. Okay, that was, and we used a synthetic design very similar to the biology. So for example, in microtubule, you know that it is GTP binding which triggers this assembly, and when GTP get hydrolyzed to GDP, it disassembles. Similarly, actin motor protein, if you look into it, ATP binding to the actin monomer, which triggers the self-assembly, and once ATP hydrolyzed to ADP, it hydrolyzes back to, disassemble back to the original material. And if you look into the way how nature does it, it's a very simple principle. From a chemist point of view, if you look into it, you have a monomer, which is dormant, that nothing will happen to the monomer unless you trigger with a chemical reaction. In this case, it's a GTP binding. In this case, it's an ATP binding. In an active state, which assembles. And there is another reaction, or a kind of, which can be an enzymatic reaction or a kind of chemical reaction network, which disassemble the GTP to GDP or ATP to ADP, not hydrolyze GTP to GDP, then the entire material disassembles into the inactive state. So from a chemist point of view, if you want to mimic something like this, what are the fuels? Again, as I mentioned, when I talked about molecular machines, we can think about enzymatic fuels, we can think about a chemical reaction, we can think about a redox reaction, because this is all fuels which are available for us, right? So, that's what exactly we try to do. So we made such a reaction-driven living and non-equilibrium polymerization. Again, if I go to the details of it, it will take 1 hour. So I'm not going to do that. But what we achieved in that process, what we achieved in that process is we can make materials which are well defined, which have a specific length, and we can, at any point, we can change its length by introducing another batch of monomers. And one is something which is important is we could make this kind of materials called transient material, which are out of equilibrium materials. As I told, most of the biological structures are out of equilibrium materials. I just wanted to give you one slide. What are these out of equilibrium material or transient materials? The beauty of transient material is, as I told, there is a reaction which forms it, and there is a reaction which disassembles it. The beauty is, you can make a material. So just look into the graph. This is a lifetime of a material. Okay, this is the non-equilibrium state. So you need a fuel for this monomer to reach this state, and you need another fuel to disassemble this state to here. So what we are doing is to make a material which has a pre-programmed lifetime. What I mean is, you can define the lifetime of a material. So in this case itself, you see that this case, it is 400 minutes stable, this is 800 minutes, and probably this is 1200 minutes. What we do is we just change these fuel concentrations which we use, and we can define the lifetime of a material. Isn't it nice? Because that's a smart material, right? If you think about it from a security point of view or any sensing point of view, this is nice, because I will come to the next slide where I explain it more better way. Because you can think about a transient or self-erasing ink, because if you make a kind of writing with this kind of inks which are transient in nature, after a while it can disappear. So this is very important from a secrecy or kind of security point of view. We can think about transient electronics. Think about a circuit which is semiconducting circuit to make an electronic devices, and you say that let it be stable only for 24 hours, and probably you can disassemble completely afterward, right? These are probably some. Don't tell me that this is not so far reached. I'm saying that these are the kind of materials we work on, and probably these are the applications one can think about. Think about a drug delivery vehicle, okay, like a vesicular structure. You load drug inside that and say that let the vesicle burst after a kind of time. Okay, so these are the probably, you can see that it gives us a possibility for us when we started thinking away from equilibrium and moving to out of equilibrium, right? Because I'm sure all the students are aware of, all of you watch Mission Impossible series of movies, and every time you see that after a secret message, the device just self-destruct, right? And probably that is probably one way you can think about transient electronics. Just short. I mean, this is not the material used in these movies. I'm saying that probably these are the kind of, just to give you a flavor, what are the advantages when one think about from moving away from equilibrium to out of equilibrium. We can think about much more nicer, smarter materials and so on. And then obviously we have to further move on, but probably I will finish in 2 to 3 minutes. We are working on further on it. As I told, always we take inspiration from nature. Obviously, the other thing is motion. Can we create this motion? Can we have a sequence-controlled polymerization? Because you know that proteins are synthesized by a precise sequence of 20 amino acids, right? So how can you have that sequence control in this kind of supramolecular polymers? And can we have motion? And then this is exactly what we are trying to do. And we have very interesting results. This is ongoing results. So this out of equilibrium materials, the assembly, disassembly process. Now you see that there are some red beads on top of it. These are kind of silica beads, fluorescent silica beads. We put it on this kind of assembling, disassembling non-equilibrium materials. You can see that is able to create a kind of force, just like actin assembly, disassembly process create a force on the cell membranes and moving cells to move, right? So this is, you can say that this is exactly what we are trying to now mimic in synthetic system by just learning inspiration from biology, just getting inspiration from biological structures and trying to mimic exactly similar process in synthetic materials. So this is the way we think, and this is the way we move. And now we are also thinking about sequence control polymerization, and we have interesting results on that. So what we are now trying to see is, as you can see, that we are trying to make a lot of inspiration from biological structures. We are now trying to think chemistry beyond the molecules. We think the dynamic chemistry beyond the molecule. So with the objective of making smarter materials, which has applications or opportunities which we never thought so far, right? And the field I'm talking about, supramolecular polymers, as I told, it's an important branch of research field right now. Probably just with 2 decades of research in this field, people realize that there is huge potential in this particular field. But where do we go? And that's one of the important questions all of us are having. So if we really want to see this material in reality, that's always I say, we need to have a kind of predictive synthetic design. What I mean is that you should be able to, like polymer we synthesize in lab, everyone should be able to synthesize this lab. So you need to provide them a kind of generalized design principles or synthetic design principle. That is quite challenging. I think probably that may happen in next 2 decades time. It's not easy, I would say. And obviously another thing is, can we use them as recyclable plastics and so on. So these are the few ideas. I'm sure probably during the interactions after this talk, we can think about more ideas. Before I stop, I just thank all my students. Wonderful. These are the pictures of the PhD students, and I have a large number of postdocs, R&Ds, and so on. And then also thanking my entire group, funding from various sources. I'm sure you would have seen this process in Rao. He started this department, and very glad that we are continuing this way. And before I stop, probably 1 minute on this, because for the students' perspective, this JNCSR provide a lot of opportunities for if any of you are interested in exploring the career in research or a research-oriented education. At various stages of your career, there are opportunities. For example, we have this integrated PhD programs where just after undergraduate program, we have both in chemical science and material science. For during the master's first year, if you want to do a summer research fellowships, there are opportunities. But obviously with a disclaimer that this is a kind of small institute, so the number of people we can accommodate is very limited. But then always I make sure that in my lab, it's all people are from Kerala, because to the summer students, because I am a person who really understood that the exposure matters, because when I started studying chemistry, I had no clue what is a career in science. Okay, and then a couple of exposure I got it, that really changed my perspective towards science. So with having known that, I'm like I try to make sure that try to give opportunity to the students from Kerala. So we even during the undergraduate program, we have something called Pose program, that is just to come during the summers and spend time all the 3 years and to work with PhD students or graduate students to really understand what is research, all to give a kind of research-oriented education. And even for teachers, college teachers, and we have a kind of 3-month summer program, and then they can come over and make use of the facilities and so on. So these are the various opportunities. Just thought it would be very useful for the student community. Thank you. Thank you for your kind attention, and please do ask some questions so that we can have a nice interactions. Thank you.
Thank you, sir, for such an informative session. Now the webinar is open for Q&A session. If anybody else like to have a direct interaction with our speaker, please come forward and ask your questions.
Or they can type in the chat box. Yeah.
Yes.
Chat box is completely empty. So,
hello sir, I'm Albish. Thank you very much for your wonderful presentation.
Thank you.
I thought the time was a little bit small for you to convey all the slides in the presentation. Anyway, I have 2 general questions regarding the creation of cell or life. What is your opinion, or what is the current stage? I'm not asking about any ethical aspect. I'm asking about the as a chemist point of view. What can we create a cell or life? What is your opinion?
So very interesting question. That's why I know that this kind of questions will definitely come at the end of my talk. But then that's why I probably at that slide itself, I made a disclaimer that my objective is not to make a cell, but to take inspiration from the cell. So if you listen carefully, I had made a statement. And then I feel that to create a cell with all its components inside, if you want to create in a kind of synthetic lab, a chemist want to synthesize this cell, I think it's still many years away, many decades away, and probably something which I would, there are interesting lectures available, why we cannot make a cell. So if you just search in YouTube, there you will be really finding it interesting lectures, why a chemist can't make a cell. Okay, so probably, yes, it's long way, I would say. and I'm not the right person to answer also, not even ethical. I'm saying that my objective is not that. I try to take inspirations from self, but I'm sure probably 100 years later we'll be thinking in a different way, but not in near future, I don't think. Yeah.
Okay, sir, one more question regarding the supramolecular polymers. I want to know whether they are rigid or flexible for applications. That's what I want to know.
Yeah, so it depends on, as I mentioned, supramolecular polymers, just like classical polymers also, we can tune its mechanical properties, like its thermal properties, Tg and Tm, where the temperature, mechanical properties can be tuned by its molecular design. So it depends on what kind of applications you are looking for. Definitely we can do it. But then let me tell you, unlike the classical polymers, supramolecular polymers should be used in those places where you need a kind of advantage of non-covalent interactions. So not necessary to be those places where you only look for mechanical properties. That's the only thing. Probably supramolecular polymers is not the place. But when I'm saying that when there is a place when you require self-healing applications or something like that, when there you require a kind of adaptive nature of your material, I think there comes the use of supramolecular polymers.
Okay, thank you. Thank you so much.
Thank you for your questions. So there is a question in the chat box. Can I answer it?
Sure, sir.
Yeah, so it's a question is from Libna Suja Shaji. Sir, what are the recent advances in your research regarding recyclable plastic or biodegradable polymers? So I tried to touch upon that, but let me tell you, so the biodegradable and recyclable, I will put it as a two different parallel streams, because biodegradable is something that you degrade it completely. Okay, you don't have to. There is no concept of recycling it again. But then again, that biodegradability is not possible for all the polymers. Even if you look into about kind of polyvinyl chloride, any vinyl polymers, and biodegradability is not easy. We cannot break that bonds. It's possible in esters and so on. So, and it's a long process, but that is very important. But then, at least from a recyclable point of view, there are more research going on right now. Recyclable plastic, not only supramolecular polymers, but there's another emerging field called vitrimers. Vitrimers is a kind of dynamic covalent bonds. That there are covalent bonds and something called dynamic covalent bonds, like hydrazine, hydrazone bonds, and so on. Imine bonds are dynamic covalent bonds. So there is a parallel field which is very active in US and Europe right now, is vitrimers, and people project that field as a kind of towards recyclable plastics, because monomers can be regenerated and it can be reused for everything. And in that context, I know the groups, at least I don't really work towards recyclable plastic at this point, but then there are groups who really explore supramolecular polymers also in that aspect. Okay, so it is happening, and right now I would say that probably there is no recyclable plastic in terms of supramolecular polymer, but it will come. I'm confident another 10 years. People are really putting into, at least the experts in this field who work on recyclable plastic say, probably in the next 2 to 3 decades time, at least 30% of the plastics can be recyclable. That's what they claim. So let's wait for that. Yeah.
What is actually the mechanism of this self-healing polymers?
Yeah. So again, question from Limna, I guess. As I told, self-healing polymers. Let me spend 1 minute on it. Already there are certain self-healing polymers based on covalent polymers. You know how it works. So you make a material, a polymer, and generally it is a catalyst-initiated polymerization. So if you take a material, you put some beads with the catalyst, okay, embedded in your material, and then if there is a crack or a kind of breakage in your system, what happens is this crack finds these beads will open up, catalyst will generate in situ. They can in situ polymerize the remaining monomers in the system. That's the way some of the commercially available self-healing polymers work. But the kind of materials I talk with you gives you a completely different opportunities. For example, in this case, there is no beads required, because if you have to increase the percentage of the bead, you are affecting the mechanical properties of the system, right? So in that aspect, you can think about a situation where you have a polymer, the monomers are always under dynamic. You just recall that video I have shown. So because the monomers are coming back and coming in. And the video where I showed a supramolecular based self-healing, when we cut into two pieces and just put it together, it self-heals because the molecules are always under dynamic. And they will always, if they are dynamic, they will try to fix the damage. They will repair the damage, just like biological systems, because they are dynamic. So the dynamicity of the system gives you the self-repairing. I hope it is clear.
Thank you, sir.
Yeah.
Okay, so there is a question from YouTube Live. If
Yeah.
we have to supply energy every time to keep an equilibrium, can we call them as smart?
No. So wonderful question. So to keep them at equilibrium, away from equilibrium, if I understand correctly, you have to put the energy to keep them away from equilibrium. So then it is, can we call it as a smart, right? I probably, you have seen at the end of my slide, there was a question mark, how to be more smart, right? I mean, like, it's not autonomous. See, if you look into nature, they're really smart, right? So when it comes to the nature, you know that this out of equilibrium, it is connected to a kind of external chemical reaction network. So this process of assembly, disassembly process, energy consumption and release of the energy happens in a kind of autonomous motion. But the kind of materials which I showed, okay, this happens only one cycle, right? You have a kind of fuel at the beginning, it goes to a kind of non-equilibrium state, it comes back. In that non-equilibrium state, it creates a kind of action. Agree, it's not as smart as the nature, but this is smarter than the existing material. But obviously what we should think at this point is to make them more smarter. In fact, we are also working on this autonomous materials, so that what we are trying to do is, again, looking back to nature to learn principles, how nature does it. Because if you try to do it in one cycle, it completely equilibrates because it's an open system, right? So what we are trying to do is create a kind of compartmentalization. That's exactly the way nature works. You create a compartmentalization, so where this kind of autonomous reactions continuously happen. Equilibration will not happen. So this is something which many people are working onwards. I hope another 5-10 years we'll have a much better material. I mean, your ideas are always welcome.
Hello.
Yeah.
Hello. I'm Dr. Bijoy. Dr. Subi, nice talk, a wonderful talk. I mean, I enjoyed it. I have a concern from the green perspective. I mean, how green is your work? I mean, let me ask you a question. Something which goes this way. I mean, have you ever think of doing a life cycle analysis of your material?
No, definitely no. Dr. Bijay, very valid question. When it comes to a kind of applications point of view, we have to really think about it. As we can see that right now we are in a stage, as I told, we are in a stage where we are trying to get a complete control on its formation of these materials. So definitely one has to look into these aspects, but I think it is too early for us. So for example, I always tell my students, I'm like, if you look into a polymerization book, okay, and if you want to write where its mechanism, where its formation, its mechanical properties, everything is written. Like if you take a book of Odian, and if you want to write a book on supramolecular polymers with complete authority on that, I think it will still 2 to 3 decades away. So my point is that it gives you a lot of opportunities. We are still trying to, because even you can see that the mechanistic aspects was evident only a few years back, and probably 2 years back is the first time when we are able to make well-defined materials with a controlled polydispersity and controlled degree of polymerization. But I completely agree to your question, a concern. Obviously, we have to look into these aspects when it comes to the life cycle and so on. How green it is definitely we should keep it in mind. But right now, our objective is to get a complete control on the material, on the synthesis of the material, on the structural properties of the material.
All right, and have you? And I have one more question. I mean, can you incorporate this with? Something like, your materials with, for example, cellulose, for example, nanocellulose. Nanocellulose is supposed to be material of the 21st century.
Yeah.
So, can you think about a composite which is with nanocellulose?
Obviously, Dr. Bijoy. So there will be a lot of opportunities. One can think about it. You can think about many of such opportunities, combining with the classical polymers, combining with nanocomposites, Definitely, that is something you can think about to turn its mechanical properties, tune its properties. Definitely, that is all open, all open.
All right, sure. Okay,
But we are not looking into those aspects. That's my point. We are our objective is to fundamentally explore this more and more and to understand this system completely. That's the way we move our research.
All right, elegant. Thank you.
There's a question in the chat. Agila Mathew, sir, what are the methods to synthesize non-covalent bonded weak bond polymers? Is it possible to have covalent, non-covalent blending? Yeah, wonderful question. The first part, again, as I told, I did not spend time much, but then as I told you, you have to use non-covalent bonds. And one of the major design principle drawback, because if you see, Jean-Marie Lehn also already started synthesizing these supramolecular polymers, but he was not successful. He was a Nobel laureate. For a simple realization that you need high association constant, then only you will get a large molecular weight system. And that, as I know that any polymeric property, large molecular weight polymers are indeed required to get mechanical properties. So that is basically the design principle. You need to find strong association constant non-covalent bonds. And you know that polymer is a single chain system, like a linear things. So you need a directional non-covalent interactions. So if you think exclusively in terms of electrostatic interactions or something, they are completely non-directional. So you may not be getting a kind of polymeric chain and so on. So there are many design aspects one has to be careful. But then once you are in the field, you learn it quickly. Okay. And the second part, is it possible to have covalent, non-covalent blending? Yes, indeed possible. So that is one way people are making. There's especially, I'm not doing anywhere, but then there's a person called Harada. Harada is from Japan. So he had made wonderful self-healing material by taking classical polymers and then incorporating this non-covalent interactions in between. And then the dynamic nature is still provided, or self-healing or memory in the polymers is provided by this non-covalent linkage, but the large polymers are providing the mechanical strength. And this is already explored. That's my point. If I wanted the question, and it is indeed possible from a material perspective. Yeah. Any other questions?
Hello, sir.
Yeah, Devadarshan. Yeah.
Yes, sir. Yes, sir.
Dr.
Sir,
Bijoy, can you mute your, just a moment, Dr.
yes.
Bijoy, can you mute your mic? Dr. Bijoy? Yeah, just.
I'm sorry. I'm sorry.
Yeah. So, Devadarshan, please. Yeah. Hello? Lost. Can you hear me? Yeah, I don't know. I think the connection is. I'm not able to hear.
Use for this.
I couldn't hear you. Sorry. Before I missed your question. Can you type in the chat box otherwise?
Hello.
I can hear you now. Can you repeat the question, please? Yeah.
Okay, sir. Could you explain about those fuels which you have said about, which we use for supramolecular polymerization?
Yeah. Sure. So wonderful. I mean, you know that, as you know that the time is limited, I wanted to give you an overview of the field rather than going into the detail into my research. So we have used 3 different things so far. And we are in the 4th one is on the going on. So we have used first, our report was like in 2016, where we used enzyme mediated, exactly similar to the actin, where we used 2 complementary enzymes to synthesize and hydrolyze ATP. Okay, so 2 phosphoryl-transferase enzymes. So that was a kind of completely biofuel. And the second one we used was a redox driven. You know that most of the systems can be assembled and disassembled by redox processes like oxidation or reduction. And the third one we was using a simple chemical reaction, a kind of a chemical reaction triggered assembly process, because especially a reversible chemical reactions like imine reaction. So that is the third one. And something which we are now trying to do it, which is very clean in terms of we don't know how to contaminate the system, is by light, because light is always non-invasive. So we are now working on light-driven transient materials and so on. So we can, in principle, as a chemist, you know that any fuel one can use to do these things. You need a clever design, that's all. Was it clear?
Yes, sir. Thank you.
Yeah.
Okay, sir, thank you. Moving to the end of the session, I invite Dr. Jyotish Kuttinappallil, Assistant Professor of Nirmala College, to propose the vote of thanks.
Esteemed speaker of the webinar, Dr. Subi Jacob George, Principal of the College, Dr. K.V. Thomas, Head of the Chemistry Department, Professor Philip Augustine, dear teachers and students. It is my privilege to propose vote of thanks to all the dignitaries and participants of this webinar. Before I proceed to my duty, I would like to congratulate Dr. Subi George for the amazing research he is doing at JNCSR. I also congratulate him for his recent achievement of the Sandiswarup Bhatnagar Award in Chemical Sciences. I share a little of his award's glory as I did PhD in the same division where he did his PhD. Today, Dr. Subi has made a clear and inspiring presentation, how he was able to control the organization of molecules, the non-covalent interactions. I hope his talk has motivated all the young aspirants of chemistry who are attending this webinar to set their goals to a higher level. I take this time to thank Dr. Subi George for being with us today in his busy schedule. On behalf of the entire Nirmala fraternity and on behalf of all the participants of this webinar, I express our sincere gratitude to Dr. Subi Jacob George.
Thank you.
Next, I thank our principal, Dr. K.V. Thomas, Vice Principal, Professor Saji Joseph, and the Head of the Chemistry Department, Professor Philip Augustine, for their guidance and support in the conduct of this webinar. Next, I thank all former teachers of the Chemistry Department who are attending this webinar, and all my colleagues at the Chemistry Department for their relentless support in all the activities of the Chemistry Department. My special thanks to Mr. Mathew Maniani, who did the live coverage of the program, and Ms. Alfie Jos, who is comparing in this program. Last but not least, I thank all the participants of this webinar for joining us today in this memorial. Thank you.
Thank you, Jyotish, sir. All of you, please fill up the feedback form for your e-certificate, and the link will be available in the chat box. Once again, we, Nirmala family, express our sincere gratitude to all participants for your support and cooperation to make this webinar a great success. We wish you a happy Diwali. Thank you.
Thank you. Thanks.
Thank you, sir.